So in this lecture, we start to talk about principal component analysis, which is one of the most common and useful techniques that's applied in genomics and in many other areas of science as well. And there are many, many ways you can think of PCA. It's incredibly flexible and useful technique, but we're going to start to think about it as a way to deal with correlated variables in linear models. And to demonstrate how dangerous correlated variables can be in linear models and how it can lead to completely incorrect inference, we'll start with this data set from the Galapagos Island that's built into R. So if you do library far away, you can get this example data set from Galapagos Island. So these are each one of these rows is a different island within the Galapagos cluster, and then you have the number of species, the number of endemics, which is the number of species that are so on some survey of the islands, the number of species that are unique to each island, the area elevation, the area of the island, the elevation of the island, the distance to the nearest island, the distance to Santa Cruz Island, and the size of the adjacent island. So we have this data set that gives you the, or I guess that's the area of the adjacent island, right? So this 1.84 here is going to line up to this 1.84 there, right? So this is a data set that we can think of as having 1, 2, 3, 4, 5, 6, 7 dimensions, some of which are highly correlated. And so again, if we type $Gala, this will give us the columns that we just went through. You can read about what endemic means or why ecologists might be interested in species that are local to a particular island at the appropriate places on the wiki. So as usual, R has really great visualization tools. So if we just say plot Gala, R will give us all the scatter plots. So there's 7, choose 2 possible scatter plots. You can do them with one of these variables on the X or the other one on the X. And R gives us both of those options by looking at either the lower triangle or the upper triangle here, the upper triangle or the lower triangle here. And so we can quickly see which variables tend to be correlated with each other. For example, species and endemics are highly correlated with each other. Well, that makes sense because endemics is just a subset of species. So it makes sense that you can't have, if you have a low number of species, you can only have a low number of endemics. Likewise, area and elevation, although not as perfectly correlated, definitely seem to have some relationship, right? So if you are lower area, you tend to be lower elevation, and then the islands that tend to have a higher elevation also tend to have a higher area. And this correlation is going to cause some problems if we try to put both area and elevation into the same model. So here I have a simple model that shows species versus area, right? And that seems to be highly significant. I get an R squared of 34%. I get a p-value of 4.0 times 4.3 times 10 to the minus 10th. But likewise, if I do species versus elevation, I also get a reasonably large R squared and a very significant model. Right. Moreover, because everything is because these three are correlated with each other, so area, elevation, and species are all going up with each other. If I just do area versus elevation, that is also statistically significant at 7.9 times 10 to the minus 12. Right. So I can put all these together in a linear model, right? And so if I do species equals elevation plus area. There doesn't seem to be an interaction term by the ANOVA. Both elevation and area come out as significant in the ANOVA, right? And so we can drop the interaction term, right? So in this ANOVA view, right? So I'm just going to go ahead and drop the interaction term. That's not significant here. So from here on, I'll just deal with the plus part of this instead of the star part of that, right? So just drop a parameter that I don't need. So in this ANOVA view, both the elevation and the area are important. But in the summary view, when I go one at a time, we can see that the area actually masks elevation, right? So if you just were to naively type this in to R without really looking or thinking about what you were doing, you said, okay, so species equals elevation plus area. Oh, well, area is significant and elevation isn't, right? But this is reflecting the numerical instability of the model. This is reflecting the fact that these linear models don't work very well when you put correlated data into them. It's not really reflecting the fact that elevation and species aren't related to each other, because if we only consider elevation and species, we would get a highly significant value, right? So we need to be careful when we're dealing with these multivariate models. We need to think about what we're doing. Right? We need to realize that when we put in highly correlated variables into the linear models, the behavior of the linear models becomes unstable and in some cases counterintuitive. Right? So there are many, many solutions to this problem. We could easily spend a whole semester, you could spend the rest of your life thinking about this problem of correlated data. But one approach that we've already talked a little bit about, so remember when we had the x and x squared and we rotated that parabola so that time and time squared were not correlated with each other. So we can take this idea of rotating correlated variables so that they're not correlated with each other anymore as being principal component, as being PCA, or principal component analysis. So to begin to start to think about this, let's make a data set that's perfectly correlated, right? So we're gonna start with a data set that's perfectly correlated, and we're gonna see how PCA is able to rotate these data so that they're no longer correlated with each other. So I just have a very simple matrix here, right? The first column is 1 through 6. The second column is just multiply the first column by 2 and the third by 3. So these are 3 columns of information that are perfectly correlated with each other. So let's think about how we might represent this table in a compressed form. Right? So clearly there's lots of redundant information here, right? So instead of representing the table like this, I could represent it like this. I could say, okay, I have one column vector, which is 1 through 6, and I have a multiplication matrix, which is 1, 2, 3, right? And if I just do matrix multiplication, I can recover the entire matrix, right? So here, instead of having to store 18 numbers, I only have to store 9 numbers, right? And if I want to recover the original matrix, I just do matrix multiplication, multiplying this by this. Okay. The rules for matrix multiplication, you guys aren't going to be responsible for this. I'm not going to ask you guys to be doing, even if we had a final, which of course we're not going to have anymore this semester. But even if we had a final, I wouldn't be asking you guys to do any matrix multiplication. But the rules for matrix multiplication, right, they're in many places here. They're in the Nieder and all textbook, right? But we just take each one when we do this matrix multiplication. We're going to sum up, right? So if I have the rows and the columns, right, I take each row. And then take this plus this times this, plus this, and this gives us this one number. So this is the way that we can, via this matrix multiplication, can more concisely represent these 18 numbers by just 9 numbers. Okay, so all that's well and good. I have a 6 by 1 matrix. I have a 1 by 3 matrix. I smush them together. I can recover my original 6 by 3 matrix. Right? But what if there's not perfect redundancy in the data? So in biology, like area and elevation in the Gala data set weren't perfectly correlated with each other. They were just really well correlated with each other, right? So now I can do what we can think of as lossy compression, right? I can still represent this data set by 9 numbers instead of 18 numbers. But now when I recover the data set, I'm not going to necessarily recover all of the information, right? So we're going to devise what we call a lossy compression strategy here, which is going to involve taking the PCA axes, right? And so just to match the way the PCA works, so PCA tends to work on mean subtracted columns. So we're going to do this very simple manipulation and subtract the mean of each column. So these are still pretty well correlated with each other, right? I have this underlying correlation. I've just added a little bit of noise to each column, so they're not perfectly correlated. And just to make the math work out with the way the PCA in R is implemented, I'm going to mean subtract these columns and work on these mean subtracted columns. Of course, if I remember the mean of each column, I can always get back the original column, the original matrix, by just adding the means back in. Okay. So now what I'd like to seek is the compressed form of this matrix. Okay. So I want to actually take these 18 numbers. I want to compress them down to 9 numbers and capture as much information as I can in these 9 numbers, in this 6 by 1 by 1 by 3. Right. So it's going to turn out that the compressed form of this matrix is going to be our first principal component. And this is going to be our first eigenvector that we're going to be multiplying the principal component by if we wanted to recover the original matrix. Okay, so this is now the compressed form of the data. And when I recover when I multiply these two together, I don't get the exact matrix back. Right, I only get right. I've lost some information. These numbers are not exactly the numbers that they are up here. Right, so this number that was 5.01 has now become 4.65, and this number that was 3.62 has now become 3.90. Right, so this is lossy compression. It's not perfect compression, but I've got most of the information back from this original matrix. So for those of you who are really paying attention, you'll notice there's this little transpose here. Right, but that just makes the linear algebra works out. So T, of course, is transpose, so it just flips a column matrix to a row matrix, or a row matrix to a column matrix. And so we want to have our 6 times 3 matrix. We want to multiply that, or 6 by 1 matrix when we get back our original data. We want to multiply 6 times 1 times a 1 by 3. And so we transpose to make that linear algebra works out so that we can smush them back together to get our original 6 by 3. And of course, you can read about how transposition works in the Niederendahl book or any linear algebra book, or you can just know that you're flipping a row matrix to a column matrix and vice versa. So we want to ask next, how good is our data compression? Right? So how much of the information do we get back? So if these 3 columns are perfectly correlated, when we go from 18 numbers to 9 numbers and then decompress, we're going to get 100% of our information back. But these 3 columns aren't quite perfectly correlated anymore, so we're going to get something less than 100% of the information back when we go from our 9 numbers to our 18 numbers. So we're going to define a sum squared error. Like as always, right, we're going to define our error sum squared, which is just going to be across our 18 numbers, the difference between the compressed and the original squared. So that's just going to be the sum of the compressed and the original squared. So I just take this number minus that number, square it, plus this number minus that number squared, plus this number minus that number squared. And I'm going to define that, of course, by the total sum squared, which is just x minus x average squared for all points in the uncompressed matrix. So I just take the average of all these 18 data points and then do the sum of x minus x average squared, which is the same total sum squared that we've had since the beginning of the semester. And 1 minus the ratio of theirs we'll call how much of the information that we capture. Right. So we did pretty well. These 3 columns are still fairly well correlated with each other, even though I've added a little bit of noise. So this compressed matrix recovers 95.7% of the data. So we've invented a lossy compression scheme that's recovered 95.7% of the data. And what actually we'll see is that PCA guarantees you is that there is no vector, there's no combination of 9 numbers that could have gotten you more than 95.7% of the data back. So there's no, at least by the linear methods of PCA, that you couldn't have done better using these parametric linear models, linear methods, which we'll see PCA is dependent on. You couldn't have done better in recovering your original data than this 95.7%. So PCA is related to, and we think about data compression all the time, right? So if you're watching Game of Thrones or whatever it is you're watching, right, you know that the Blu-ray looks better than the DVD, looks better than the MP3 that you maybe download to your phone because the MP3 is more lossy compression. Right, so as you put more data in, when you uncompress your movie to watch it, if you're looking at a larger file, it's higher resolution, right? When you stream the high resolution option from Google Play, it looks better than the standard definition because that's a larger file. You're getting more information, right? So this number, it's the same idea of the higher this number is, the closer we got back to our original data. So again, to start to introduce the formality of principal components, right? You start with this original matrix, right? The idea here is that you're compressing these 3 columns into 1 column. The best that you can do from that 1 column, the best compression that you can get using the linear methods under PCA is this column here, which is we'll call our first principal component of this matrix. And we say that component explains 95% of the data. Right. So if you were to uncompress, right, if you consider this as the compressed form of the original matrix, if you were to uncompress based only on this first PCA axis, you'd recover 95.7% of the data. So we say that this first PCA axis explains 95.7% of the data in the original matrix. Right. So again, and you can think of that as if you were to use this column to uncompress. To recover an uncompressed version of this 18.3 under lossy compression, even though you only use this first column, you'd still get back 95.7% of your data. Okay. Now we can improve the compression if you use more data, right? So just like when you download the high resolution version versus the standard resolution version of Game of Thrones, that's a bigger file, so it looks better, it looks sharper, right? You get more of the original film or more of the original images and sound by using a larger file. So if we instead use both of these columns, if we had a data compression scheme that involved both of these columns, we need more memory in order to do that, right? Because now our data compression is going to require us to store these 12 numbers and not just these 6 numbers. But we're actually going to be able to get 99.8% of our data back. So what this looks like in practice, right? If we're storing our data in these 2 components, right? And when we rotate these back, when we take these data, and rotate them back to get our original data, and then form this error sum squared, we actually capture 99.8% of the data. Right? So if instead of just using one column to represent our data, we represent two columns to represent our data, when we rotate the data back and calculate this error sum squared, we get 99.8%. So, or with much less typing, we can get this number here, right? Which says that if you go from a three-dimensional space, your original three-dimensional space, to a two-dimensional space, when you rotate back to the three-dimensional space, you can recover 99.8% of your data. Now, of course, trivially, if you use all three components, you get 100% of the data back, but that's essentially just copying the data. It's like that's essentially taking the data set, rotating it to a new three-dimensional space, and rotating it back to the original three-dimensional data space. And of course, that rotation, if you don't lose any information if you just rotate it and rotate it back, so you get 100% of the data that way.